Hello, everyone. How is everybody doing? Welcome to our first UEI Masterclass. I hope everyone is weathering this current epidemic or pandemic. I'm Eric Urtet with UEI, and today we'll be covering advanced hardware and synchronization. This is meant to be somewhat informal with a Q&A session to cover various concepts. So here is our quick agenda. First thing, we will review 1 pulse per second schemes, review some code, and open it up for the first round of questions. And then we will review Precision Time Protocol, or PTP, also known as IEEE 1588, synchronization, and compare that to the previous one, PPS. Please enter your questions using the chat box, which is on the bottom of your screen. You should be able to hover down there and see a chat box pop up, and that should do it. On hand, we've got a whole bunch of resources for you. The UEI Applications Engineering team, as seen here, they will answer your questions and display examples as needed. So from the top, they are Timur, who wanted everybody to know to live dangerously by using AutoSet on your oscilloscope. Then we have Austin, who's an application engineer with more than 5 years of data acquisition and control experience with embedded devices. He is an avid hiker, but apparently a terrible flight simulator pilot. And we have Phil, who has been working in the autonomous and embedded industries, helping customers select and deploy technology around the world. He is also known for his balloon animals. My kids love them. Then we have Brian, who is the type of guy who, when you send in the question, he seems to have all the answers. And then, of course, Prabhu, who is on the other side of the pond in the UK. He really has nothing to offer other than solutions, workarounds, and fixes. His mantra, of course, is keep calm and carry on. So that is our team today. Austin will be reviewing all the synchronization concepts. Take it away, Austin.
Awesome. Thank you, Eric. So as Eric mentioned, my name is Austin Turner, and I'm an application engineer here at UEI. So what we're going to go over today is some of the tools and methods that we provide here at UEI to synchronize not only the boards within a chassis, but to synchronize across many chassis and many boards within a system. So let's see. Eric, it looks like you need to cancel the sharing screen, and then I'll be able to share mine. Okay, so what we're going to do here is we're going to take a look at some of the videos that we have for synchronization. So we'll go to our resources here. And we'll take a look at this here. So let me share my computer sound. And just a heads up for everybody. I don't have control over the audio sound from the video, but it is quite loud. So I'll give you a minute now to adjust your volume, lower it so it won't be screaming loud in your headsets or from your PC. Okay, and so let me start up this video.
For many reasons, you may want to synchronize your I/O boards. This could be all the I/O boards in a single chassis, or multiple boards across multiple chassis. To synchronize the I/O boards, all their sample clocks must be equal or derived from the same clock. For external clocking, you can directly feed in a signal at your desired sample frequency to the sync connector on one or more cubes or racks. Routing this clock to all I/O boards will provide equal sample rates across the chassis. The other option is to supply a 1 pulse per second signal to all the IOMs. The 1 PPS can be generated externally, for example from a GPS, or internally by the IOM itself. And this will tame the sample rate clocks. This method also allows for 2 features. 1, the ability to have different sample rates on different I/O boards. And 2, the ability to internally sustain a clock if the external signal becomes disconnected. Let's take a quick look at the internal workings. An adaptive digital phase lock loop, or ADPLL, on each IOM will use the external 1 pulse per second signal to generate and maintain an internal 1 pulse per second signal. This allows a UEI chassis to stay synchronized in the event of a wire becoming disconnected, or if the 1 PPS signal is lost or interrupted. The ADPLL then routes this 1 pulse per second signal to our event module. The event module generates a clock at your specific frequency, which is derived from the internal 1 pulse per second signal. There are also 2 event module dividers that can take the output clock from the event module and use an 8-bit integer to divide the clock rate down to a smaller value. These clocks can then be placed onto the backplane for any I/O board to use. Then each I/O board is able to divide down these clocks, providing a very flexible way to acquire multi-rate data. So you see, using the 1 PPS approach provides you with a fault-tolerant, flexible solution to clocking multiple I/O boards across 1 or more chassis.
Okay, so you might want to turn up your volume once again so that you can hear me clearly. But now what I'm going to do is just kind of go over some of the questions that came in while the video was playing. And if you have any more questions, please send them in through the chat. So let's see, what's one of the questions that came in? Okay, so the first question is, how do I generate multiple rates for different boards in a chassis? So the video went over it a little bit to say that we generate a clock within the chassis, and we can divide that clock down with an 8-bit divider. So then we distribute that clock to different boards. Now we're a little limited by this because we only have 4 sync lines. So if we need 10 different clocks, well, we need a different method of achieving this. So what you can do instead is you'll generate some clock, say 1 megahertz, and on each board there's a 32-bit divider. So that basically allows you to get almost any arbitrary sample rate for each board that is still using that synchronized clock, because the clock that we've now generated is, as we mentioned, tamed by that 1 pulse per second. Okay, so hopefully that answers that question. The second question is, how do I avoid different trigger times between chassis? That's a great question. So the idea here is that over a distributed network, if you were just to send let's say a broadcast to say trigger now, how do you know that all those packets are received by each chassis at the exact same moment? Well, you wouldn't. There's too many non-deterministic delays within a network. That could be through queues in the PC itself, or queues within switches and routers. So the way that we avoid this is actually triggering on that 1 pulse per second. So the way it works is you'll still send a broadcast command, but you'll say trigger on next 1 PPS. So what that does is we can read when the last 1 PPS occurred. And let's say it occurred, just about 0.2 seconds ago. That means we want to send the broadcast command right after it happened. We have a large window of time, that 0.8 seconds before the next one. And now we know all of our chassis are going to be triggering at the exact same time. Okay, I see a few questions coming in live here. So one question is, does the 1 PPS only need to be given initially? And would it need to be continuously applied, or is it ignored after the initial pulse? So the 1 pulse per second, the way that our system works, it should be applied consistently. The reason for that is when you're trying to synchronize multiple chassis, they should be using the same clock reference. So if you have that 1 PPS at the start, that means they're all going to be using the same reference. If for any reason that 1 PPS is lost, we internally generate a 1 pulse per second so that, yes, your data acquisition will still occur, nothing will be interrupted. However, since it's not using the same clock reference, there will be drift between different chassis. So really maintaining that 1 pulse per second throughout the data acquisition will ensure that everybody's using the same reference and that there's very minimal drift between the chassis. Okay, let's see, another question that came in. Is it possible to sync the chassis and set their internal clock so that a rough sync within about 50 milliseconds can be maintained after power cycle when recording locations across the system are physically separated and impossible to connect, but needs to be roughly synced up later on? So 1 PPS really has in mind synchronization where you can directly connect different chassis. There's other methods of synchronization that you can use. One would be precision time protocol, which we'll look at later. But what might apply better here is either using GPS or iRig synchronization so that each, we'll go with UEI cube here. So each cube would have a GPS module that it is now synchronized to. And that GPS module could be using the 1 PPS method as we've mentioned before. All right. So next question is, how is 1 pulse per second configured on your boards? Well, that's a great question. Let's take a look at some example code. So I think I'm still sharing my screen here. So when you download our PowerDNA software, and that is free to download at any time from our website, you will get this example code. So let me navigate here. So into PowerDNA, SDK, examples, and we'll look at the low-level C code. So as we can see, we have many examples here, whether it's analog inputs, outputs, ARINC, CAN bus, counter timers, etc. What we're looking at specifically is synchronization. So we have a folder of those examples. So we'll take a look at the 1 pulse per second, and we'll wait for Visual Studio to open up. And it came up on this screen, so once it loads, I'll move it over. So the idea here, though, is with 1 pulse per second synchronization, you're really configuring a synchronization scheme. So that is a scheme that's used on the system itself. And by system, I'm talking about a cube or a rack. So once you set that synchronization scheme, then you'll go through and you'll configure each board to set its clock rate, set its timestamp rate, and also set where its trigger is coming from. So I won't go into the details about some of the specifics at the beginning of the code because those are generic and we've tried to keep those consistent between all of our code. So you can take a look at the other code to get an idea of how that's usually oriented. So what I'll go down to is this sync scheme 1 PPS master. So let's see. I don't know if I can. So a question came in, would be better if I can change the background to white. I'm not sure if I can easily configure that on the fly. I'll send you this example code right after. So let's see here. So with the 1 pulse per second master, we're going to set the sync scheme to the device that we're using. And then we're going to set the sync source to 0 because we're internally generating it. We are configuring it for a 1 pulse per second. And then this is the accuracy that we expect for that 1 pulse per second. Now our synchronization will be much better than this, but this is to say if for any reason that external 1 pulse per second is out of this range, then we're going to use our internal 1 pulse per second as the master now. And so that's in case for any reason that 1 pulse per second is lost. So we'll kind of briefly go over this. This is the sync server. So we're creating a 1 pulse per second and we're going to route it out of our sync connector. We're going to use our event module. And with that event module, we're going to route that to our second sync line. So we have 0, 1, 2, and 3. And here's the frequency that we're going to generate. We're also going to use a trigger. And as I mentioned before, we're going to set that to the 1 pulse per second trigger scheme. And so let's scroll down until we actually get to, so we're setting up what we call our VMAP data acquisition. If you have any questions about VMAP, please send those in. But this is one of our acquisition modes. So we've gone through, we've set up our VMAP, and now we're going to define our sync scheme. So this example is showing 1 master, 1 slave. So we're going to set up 1 for master and 1 for external 1 pulse per second. So after we've done that, now we're going to go through, and as I mentioned, we're going to define the layer clock, the layer trigger, and the layer timestamp. So in this example, we're using the exact same clock to actually clock the board and to clock the timestamp. Now you can change that if you need a higher resolution timestamp, but this is just an example, so feel free to tailor it to your application. We're going to call this function right here after we set up all of our synchronization because we want to make sure that if we're using an external 1 pulse per second, that we've truly locked onto it and become fully synchronized. And then after that, as I mentioned, we're going to trigger on the next PPS broadcast. So directly after a 1 pulse per second has occurred, we're going to send this command, and now all of our chassis will trigger at the exact same time. Okay, let's see if we have any more questions. So is there a synchronization chassis? I will so there goes in the other end that and then there's multiple there, and then another question. Yes.
Hi, everyone. This is Eric back. We are going to wait 1 sec to see if Austin will come back. I don't know why I got disconnected. Welcome to our virtual world that we're living in now. I will try and pick up a couple questions if I could. I'm just going to leave this slide on there until we can get Austin back. One question was, how do we connect all of our hardware together? And we do have a piece of hardware called the DNA STP Sync 1G terminal, and that terminal allows you to connect our synchronization port across all of our different pieces of hardware. And it certainly works very well. I believe after this, we were going to cover 1588 or PTP, which is a method of synchronizing everything using basically your standard Ethernet cable. So I am going to wait just a little while longer here because I am certainly not the expert on this.
Hey, Eric.
To see if Austin will reconnect.
Eric, can you hear me?
We can hear you, Austin.
Great. It looks like we had a slight technical difficulty, result of being on the Wi-Fi, and but it looks like everything is back up.
Do you want me to pass it back to you, sir?
It looks like I can take over, so I will do that.
Oh, perfect.
Okay, so let's see. I'll repeat the last few bits that I went over, just in case. So the idea here is we set up the sync scheme, and then we define each board for where it's getting the clock, trigger, and timestamp. When we've done all that, we want to make sure everything's stabilized, and we've locked on to the external 1 pulse per second. And then we're going to trigger on the next pulse per second broadcast. So that's going to occur, we're going to call that right after 1 PPS has occurred, so that the next 1 pulse per second, everything will trigger the exact same time. So we've covered any delays throughout the network. All right, so let me see here. Okay. So we'll go into the next video and we'll take a look at 1588 synchronization. And so once we go over that video, we'll jump into more questions again. So let me, again, share my computer sound. And once again, I want to give a warning that the video can be quite loud. So you want to adjust your volume. So I'll give you just a moment for that. Now let's jump into this video. Okay, so that was, a quick view of 1588. What I want to do now, though, is show the comparison of why someone would choose between 1588 and 1 pulse per second synchronization. So I think that'll cover the question that had come in of, is Ethernet better than the sync cable? So really, synchronization over Ethernet is going to be based on IEEE 1588, whereas using our sync cable, you're going to be using synchronization, over the sync cable that we provide with that STP Sync 1G.
Distributed systems often require synchronization to align data gathered from a variety of sources. UEI provides hardware and software solutions that implement two common synchronization standards. The 1 pulse per second system begins with a source to generate the 1 PPS electrical signal. This could be generated by a GPS receiver, an iRig timecode generator, or internally by any of our CPU modules. To simplify 1 PPS distribution, UEI offers an STP sync board, which connects the 1 PPS across multiple chassis. Larger systems are possible by daisy chaining additional STP sync boards. This system ensures that all sync signals have gone through an identical buffer and that no buffer-induced timing skew is introduced. The Precision Time Protocol uses an external device called an IEEE 1588 Grandmaster clock as the source for the sync. The Grandmaster exchanges PTP synchronization packets over an IPv4 UDP Ethernet connection, allowing for fine-grained synchronization over a local network. Slave devices receive the PTP packets, determine network latency, and derive local synchronized reference signals from timestamp data. This allows all devices in the system to be synchronized with each other. Both systems effectively perform the same function, but each have their advantages. The PTP system automatically and dynamically selects the best Grandmaster clock at all times, auto-compensates for distance and network delays, and PTP runs over Ethernet cables, all of which make for an ideal choice for distributed networks. The disadvantage of this system is, one, it's dependent on the master clock, typically an expensive piece of external hardware, and startup takes considerably more time than the 1 PPS system. The 1 PPS system, by comparison, doesn't need that expensive Grandmaster clock. You can achieve it with your existing UEI hardware. And unlike the slow startup time of the PTP system, data sync can begin almost immediately using 1 PPS. And while it's possible to daisy chain large numbers of chassis, the data sync can skew over long distances. So depending on your application, one of these options can be used to synchronize the data collected, giving you precise timestamps of when events have occurred.
Okay, so I'll give another minute for everybody to turn their audio back up to hear me again, and I'll go over some questions. So the first question that has come in: how can we know if a rack is actually PTP synchronized? So there's a few methods of recognizing that the rack is PTP synchronized. One is you can grab the latest UTC time that has come from the Grandmaster. So with that, you can see if there's any stale data that's there. If it's stale data, then you know that you've lost a connection to the PTP Grandmaster. Another part of PTP is we track the number of packets. So with the same idea, if the number of packets that have come through over PTP, because that packet counter is specific to PTP, if that value isn't incrementing, then you know you've lost that PTP synchronization. So another question: can you do 1588 over Wi-Fi? This is a great question. I don't have exact answer. We've never tried it. One of the parts the beauty of 1588 is that you can do an end-to-end network delay and compensate for that network delay. The problem is it doesn't take into account both sides of the network delay. And it believes that the forward and the, I'm going to call it backwards delay are equal. So when you go over Wi-Fi, there's more of a chance that those are not equal. And if they're not equal, then your synchronization using 1588, it may be possible, but it will probably be less accurate. Another question that's come in, what is the highest precision reachable using timestamps from PTP at acquisition time by layers? So part of the precision of PTP is how precise is your grandmaster. So if you use one of the, what we use here is Symmetricom grandmaster, that's going to be a very precise PTP grandmaster. And so locking onto that, we will now be in the tens of microseconds of precision. Depending, again, on the grandmaster that you have, that may differentiate how accurate your timestamps will be to the actual time of day. So another question came in, which version of PTP do you support? So we support 1588, 2008. It's also known as PTP version 2, and that is over UDP or IPv4, so we don't support the IPv6. One question came in, does the PLL lock to the input signal? I'm not sure what's meant by that question. So I'll talk about some of the mechanics behind how we do our PTP synchronization. So with PTP synchronization, what you really want is hardware timestamping. So that allows right before the packet is sent, the actual hardware is incorporating a timestamp into the packet. So with our PTP synchronization, we're using hardware timestamping. That way we have the most precise, most accurate way of using PTP. Once we have that PTP time, we actually still use a 1 pulse per second internally. So what that means from our API is that you're going to configure the PTP scheme, and once you do that, all the other API of setting up a clock, trigger, and timestamp are going to be identical. Another question came in. Let's see. Can the PPS have a sample time shorter or longer, 1100 or 800 milliseconds, than true clock time 1000 milliseconds? This is for simulation purposes. So I don't know the exact answer to this, so I'll have to do some research. I believe the answer is yes. So the way that we can handle different, almost periods here is by changing that 1 pulse per second accuracy within our code. So I want to verify this, but I believe this is the value right here that we'll be able to change and increase it enough to handle those 1 pulse per seconds that may have some shifts in period. Okay, so another question, let's see. Can we use regular switches in the network with PTP? I would say you can. It's only possible when the end-to-end delays are being used as a mechanism to calculate the offset or the network delay, but it's not advised. And that's because I've mentioned earlier in this masterclass that switches and routers have queues, and they're non-deterministic delays. So what that means is the delay could be constantly changing with those non-PTP capable switches. And I think that's that'll probably answer this other question that came in. What's the difference between a boundary clock and a transparent clock? So on a PTP network, you'll have a grandmaster and you'll have switches. So the way these switches work is one of two ways. They can be a boundary clock in which they will take in that grandmaster, and then all of their other ports will be acting as master ports. So that way they are tracking the grandmaster that's used on the network, and all of the slave devices believe that that switch is the master. And then a transparent clock would be a little different in that it is almost as it sounds, that the switch is transparent. So it's taking into account the time that the packet sits in its queue, and then it's sending that packet out with a new timestamp, but still keeping the same grandmaster. So it's not, making believe that it is a grandmaster. Let's see. Another question came in. With Meinberg grandmasters, we can distribute PTP, IREG, PPS normally synchronized. What is the best way to handle data then, particularly if you need time comparison between signals acquired by several chassis? That's a great question. It really depends on how you want to configure your network. If you're okay with the capital that you need to invest for a PTP capable network, so that's the PTP grandmaster, which it sounds like you have, but also PTP capable switches, then PTP might be the best way to go. So it won't have the most accurate compared to 1 pulse per second. 1 pulse per second will definitely be more accurate. However, it might be easier to distribute Ethernet rather than these RJ50 connectors and our sync panels as well. Hopefully I've answered that question there. Let's see. Would you say IREG-B or PTP is better accuracy? Again, with PTP, it really depends on the grandmaster. There's different classes for each grandmaster. So with the highest class of PTP, maybe it's using GPS, so the grandmaster would be using GPS as the main clock, and then sending out all that data over PTP. In that case, it could definitely be more accurate than IREG. Okay, another question. Is the embedded NIC, network interface controller, on the chassis compatible with hardware PTP version 2? Yes, so that is what we support. We support hardware timestamping with version 2 of PTP. Right. Let's see. Looks like the questions keep coming in. This is great. When you use 1 pulse per second, does cable length matter? Yes, and that is a big differentiator between PTP and 1 pulse per second. So PTP can calculate for the network delays. 1 pulse per second, what you really need to do is to have the same cable length between all devices. That way, that 1 pulse per second has the same delay included between all devices. Now, you're relying on the cables being completely identical. I think for our purposes, within a couple hundred feet, they should be identical enough where If they're the same length, you should have the same delay, but cable length does matter. You will need to match the cable length between all devices. Okay. How long is the Grandmaster startup time? Oh, so this is a multiple part question. So how long is the Grandmaster startup time? Is there a list of known preferred compatible Grandmasters? How are timestamps returned to the control software? Are absolute timestamps known for each sample returned? So part of this, I think I should jump into some code and give an example of how we configure the chassis for PTP. So again, jump to synchronization, and we'll go to PTP synchronization. One question that had come up in the background is, oops, let's see here. What is the max sync cable length? I don't know the answer off the top of my head. I believe we tested with about 200 to 300 feet of cable, but I'll have to get back on the exact answer for that. So going back to the multi-part question, how long is the Grandmaster startup time? So if you're talking about from our components, it really depends on the network of who we're connecting to, and how many devices are we connecting to for everything to become synchronized. Our Grandmaster itself will take about 1 minute to 2 minutes to realize that there's no other masters on the network that are better. So part of 1588 is this best master clock algorithm that is constantly running and deciding which Grandmaster on the network is best. So since our chassis can be a slave or a Grandmaster, that means that we're going to be listening at first, and then if there's no other Grandmasters on the network that are better, we're going to become the Grandmaster, and that should happen within about 2 minutes. You can also statically define who the Grandmaster is. So you can do that over our serial port and set those as a static configuration, or you can do that through our API as well and set that up to a preferred Grandmaster. And so how are timestamps returned to the control software? So again, we're going to run the software. Timestamps are going to be based on a clock. So it's just going to be a 32-bit counter that increments based on a synchronized clock. So the way that we correlate it back to actual time of day is, again, we're going to trigger on that next pulse per second. So when we trigger our next pulse per second in PTP, that's an actual 1 second of UTC time. So once we know the time of day that we've triggered at, that will be timestamp 0, and all timestamps from there on will be incremented by that synchronized clock. So for example, if we want to trigger at, let's say, 10 o'clock, so we're going to call the sync trig on next PPS broadcast right before, right at 9:59:59, so that at 10 o'clock we've triggered. So timestamp 0 will be 10 o'clock, and all timestamps will be incremented by that 10 hertz clock that we've set as a timestamp. Let's see, so I think I've answered that multi-part question. And please, if you have any more questions, if we don't get to them here, because I think we have to wrap up soon, please feel free to contact us over email. So I think I'm going to take just a couple more questions here. Is it possible to know the level of synchronization stratum actually reached by the chassis during runtime? I don't know that answer off the top of my head. I'll have to do some research about that. So let me write that down to look up the, can we know the stratum? So I do know that we can 100% know which grandmaster we've connected to because we can get the grandmaster MAC address. When we know the MAC address, well, hopefully someone knows who that MAC address corresponds to, and then we'll know who we've actually synchronized to as well. All right, so I think I'm going to take just one last question here. We experience dropout occasionally. Can you recommend a cable for increased signal integrity? So that really depends on which synchronization method we're talking about. If you experience dropout occasionally with 1 pulse per second, we'll just want to look at how you have your cables connected. Are you using the STP Sync 1G that we have? Or maybe you've got your own method of connecting those cables. Let's see. And another idea is for long lengths of cable, you might want to have that STP sync in there as almost a buffer. And so that'll make sure that the signal isn't dropping out before it gets to our device. And then for PTP, really the signal integrity should be maintained because it's Ethernet. Ethernet will have its own standards of how far it can travel over. And if you follow those guidelines, then I think you should be okay. So with that, I apologize for dropping out earlier. Thank you for your time. I hope this was educational for you as well as it was for me. And again, thank you for your time. So without further ado, Eric, if you'd like to take over.
Oh gosh, Austin, this was great, and thank you everybody for participating. Obviously, this wouldn't be very fun at all if nobody was around. So we will be contacting everyone with unanswered or partially answered questions, as well as sending out a follow-on email with some of these resources. If you have any more questions or need support, on the screen here, we've got our email address, support@ueidac.com. They go to the group. So everybody who was talking today and participating will be in that group and we'll be able to answer your questions. We will be continuing the UEI Masterclass series, same time next Thursday. We would love to see you all there and more. We will come up with some more topics, and hopefully this was certainly worth it. Until then, please stay healthy out there. Thank you.